So we come towards an end of our earth science curriculum. We need to now bring together the grand unifying theory of earth science called plate tectonics. Plate tectonics evolved through the 20th century and is now a well accepted and well documented part of our understanding of how the dynamic earth changes through time and how the plates that we see in this map cause earth events that prior to that were not well understood in terms of cause. This slideshow will be more or less a history of the theory with details of how this theory has evolved. And when we look at this map, we can see that here we are on the North American plate in the east coast of the United States. This would be called, where this continent meets the ocean, is called a passive margin, because in terms of plate tectonics, not much is happening there. The action of plate tectonics is where the plates meet. And in this case, they're not coming together, they're separating. Where these arrows show them moving in opposite direction, the plates are separating. So all along through Iceland and through the Atlantic Ocean basin, plates are separating from each other. But if we move over into the Pacific, we note that there are plates coming together. Along this boundary, first the Antarctic, then the Nazca, then the Cocos, and the Juan de Fuca plate are all colliding along this region of the Earth. And then if we go along the Alaskan archipelago, we see the Pacific plate colliding with the North American. The Pacific plate colliding with a little tongue of the North American. The Filipino plate in between here, with no motion indicated on this particular map. Here, the Pacific plate colliding with the Australian plate. Again here. So we see two types of motion so far, separating, colliding, and then here on the southwest coast of the United States, through LA up to San Francisco, we see a transform plate where two plates slide next to each other. So those are the three major motions of plate tectonics. We now know that the movement of crustal plates over the surface of the Earth causes earthquakes and volcanoes. And if we look at this map, we see that so many of the earthquakes and volcanic activity follow the margins of the plates, where the plates are meeting, through the Atlantic Ocean basin, along the coast of South America on the west side, the west coast of the Mexican and Isthmus of Panama, up the west coast of the United States, over to here in what is called the Ring of Fire. That would be this connected to this around the Pacific Ocean basin, the Ring of Fire. So once what this was understood, things fell into place pretty beautifully. So continents appear to fit together like a puzzle, right? That was one of the first insights that naturalists, earth scientists, there were no such thing as earth scientists in those days, but maybe geologists first had an inkling of, was that when you look at a map of the world, it's sort of oddly symmetrical, particularly between the South American coast and the African coast. Seems to be some kind of connection there. So back in 1596, there's a Flemish mapmaker, Abraham Ortelius, who notes that the coastline of the continents appeared to fit together. He suggested that the continents were once joined and that the Americas were torn away from Europe and Africa. Then, 40 years later, Danish anatomist and geologist Nicholas Steno, who spent most of his life, I think, down in Rome, proposed the law of superposition. Each layer of rock is older than the one above it. This concept evolves into an understanding of stratigraphy, how, say, sedimentary rock layers are connected and correlated across great distances, both horizontally and then vertically, and then you can connect them in time through fossil content. So This is a beautiful new insight into the way in which the Earth divulges its antiquity. But it's another, really, almost 300 years before real progress is made understanding this relationship between the continents that appear to have been stuck together, this insight that was, from the 16th century. And that's 1912. A German meteorologist and geophysicist, Alfred Wegener, proposed that the continents were once joined in a supercontinent called Pangaea, and you learned about this in the 6th grade. And that Pangaea's constituent portions, the parts, moved thousands of miles apart over long periods of geologic time, a phenomenon he called continental displacement, now known as continental drift. And even though there was strong fossil and stratigraphic evidence, his theory was rejected because he could offer no mechanism for why the drift would happen. The evidence can be seen here in this beautiful little map showing South America and Africa connected, Madagascar, India, Antarctica, and Australia, all connected, and connected in a manner that relates to the fossils that have been found on each of these continents. Here, with the green, we have a fossil of what's called Glossopteris, which is a plant. You can find the fossil of this plant on the Australian continent today, Antarctic, Indian, Madagascar, the island of Madagascar, Africa, and South America. How could a single plant's remains have been deposited on all these different portions of the Earth that are so far apart from each other if they were not at one point connected? There's no other explanation. Then you have the fossil remains of a freshwater reptile, Mesosaurus. Well, how does that reptile get from Africa to South America across the great Atlantic Ocean basin? So, Wegener's perception that something is strange here, finding these fossils in these different places, is accurate, but he can't explain how the Earth changes from this supercontinent to the world we know now. This would be a fossil of Mesosaurus, and this fossil has been found. There's more than one of these. And here are the Glossopteris tree leaves. These ones were found, these are from the Permian, and it looks like they were found in New South Wales, Australia. So this is some kind of sedimentary rock from the Australian continent, but they have been found again on those other continents as well. Then, if you go to the Museum of Natural History, they love to tell the story of this type of sandstone called the Old Red Sandstone, which has been more or less understood to have existed on the same continents that are now, and those continents now separated. So the point here is that when there was Pangaea, there was a mountain building event, the Caledonian Mountains. They rose up high above sea level because of colliding plates, and then slowly eroded. And they eroded into basins at their base, leaving behind thousands of feet of sediment, which became a red sandstone now millions of years later, when the landscape has been pushed up and that rock has been exposed. And we find that rock in Scotland, in Norway, in Greenland, in New Brunswick, up in the Maritimes of Canada. Is that right? New Brunswick? I don't know, now I'm thinking, or Labrador, but it's up there north of Nova Scotia. Then we find it in the Atlas Mountains of Morocco, the Iberian Peninsula, everywhere that the sediments were deposited when the continents were together. So here's the old red sandstone in Scotland, and this would be an equivalent bed of a similar red bed found in New York State in the Catskills. So the evidence that I now find, or the support for this theory that this is actually the same rock as this, seems weak. But the basic idea, I think, is still accepted, that there can be rock units that were formed together when the continents were together, and now can be found in these widely disparate locations, widely separated locations. This would be a map of where these rocks, this old red sandstone, is now found if we looked at a map of the Earth today. And this would be the Maritimes of Canada, this east coast here of Greenland, Iceland, Norway, down into the Baltic, British Isles, and Ireland, Iberian Peninsula, and the Atlas Mountains of Morocco. In 1929, a British geologist named Arthur Holmes proposed that convection in the mantle is the force driving continental drift. So we've talked about this. That is that hot material in the mantle rises because it has low density, and then it cools and turns, and at the points where it's turning, it's separating, pulling apart the plates above it. Although his ideas were not taken seriously at the time, Holmes' mantle convection hypothesis later gained support. By the 1950s, oceanographic vessels mapping the ocean floor provided data on the topographic features of the ocean basin, leading to the discovery of mid-ocean ridges. These underwater mountain ranges encircling the planet have formed as the Earth's plates separate. So this would be then mantle convection up to the asthenosphere, which is acting like the oil on the top of the pizza under the cheese. The cheese is the solid rock, the continents or the ocean basin, and the oil under, between the sauce and the cheese, is what the continents are sliding on. And of course, they slide until they're pulled back down, cooled and pulled down, where they heat up and rise again, pulled down. So here are places of collision where we have earthquakes and volcanoes, and here are places of separation, which right now on the Earth we generally find in the ocean, although there's one place in East Africa where this is also occurring today, where a continent is splitting apart. Here would be your Atlantic Ocean basin with the mid-ocean ridge, and it is at this location that the two plates, the European plate, the African plate, 3 plates actually, and the North American plate, are separating. Now, one of the things that people were able to do once they got out on ocean vessels is to start to drop devices into the ocean so that they could collect the rock at the bottom. The rock at the bottom tells a story. Let me just quickly just give you a sense that this is how, if you were to start sailing across from, say, New York City across the ocean, you would have beneath you first what's called the continental shelf, and near the land you would have sands that have been deposited. Those are the biggest of the small particles. Then silts and shales deposited. Then clays and shales. And now we're off. This might be, easily 100 meters deep, maybe even deeper than that, 500. Clay and shale moving out. Maybe as you went further south, you could get some coral developing in limestone waters down near Florida. And then this continental shelf slopes down. Along the slope, you get slumping sediments that are called turbidites. Then you get out onto the abyssal plain, which mostly has got very little clastic fragmental sediment from the continents, but does have debris from organisms whose bones and the like have settled. So this is what we've just looked at. The continental slope, the continental shelf to the slope, out to the abyssal plain, and then as we go out further, eventually we would see this mid-Atlantic ridge. These are interesting forms which continue up into New England. These would be like seamounts and are injections of intrusive igneous rock that continue up into Maine and New Hampshire and are form what are called monadnocks. So, in 1960, American geophysicist Harry Hess, seen here when he was in World War II, mapping the ocean because we were afraid that the Japanese or the Germans would find places to hide with their submarines and attack our shipping. So we wanted to know what the bottom of the ocean looked like. That was our motivation initially. Well, Hess spends his time during his period as a naval officer. He's also a professor at Princeton. He's developing the idea that oceanic crust forms along mid-ocean ridges and spreads out laterally away from the ridges. The following year, geophysicist Robert S. Dietz named the phenomenon seafloor spreading. Hess and Dietz's work played a pivotal role in the development of the modern theory of plate tectonics. And here you would have continental crust splitting with magma rising from convection, the crust beginning to split apart. This is how Pangea would have split apart, and this is actually happening in our region of the Earth. This is one of the explanations for the presence of the Palisades Cliffs and the Watchung Ridges, which are out in New Jersey. Three zones of extrusive igneous rock that came up with the rising convection cell. Formation of a rift valley, which then is filled in with ocean water, and eventually we got our Atlantic. That would be the older ocean here, with old ocean crust at the outermost edges of the ocean basin and newer ocean crust still forming at the middle. 1963, British geologists Frederick Vine and Drummond Matthews, as well as Canadian geophysicist Lawrence W. Morley, who worked independently of the others, postulated that new crust would have a magnetization aligned with the Earth's current geomagnetic field. That is, as rock formed, as a basalt formed. I moved all the rock away. As a basalt, this is obsidian, but we'll just say, let's say this came out as lava. When it freezes with the geomagnetic orientation of that moment. But what if the geomagnetic orientation of the Earth, the North and the South Pole, change over time? What if we know for a fact sometimes north is south and south is north? Well, then you should be able to see that in the frozen rocks that you could collect moving further apart from the point where the rocks are spreading. And that is exactly what these gentlemen did. They collected rocks moving from the mid-ocean ridge towards the shores of North America, the shores of Europe or Africa, and they figured out that there was a definite flipping of magnetic polarity, which indicated a flipping on either side, equally far apart from the zone of spreading. So positive, negative, top of my hand, bottom of my hand, positive, negative, top, bottom, on either side of the mid-ocean ridge. But then move away 200, 300, 400 miles. Suddenly we have negative on the top and positive. Now move away further, flipped again. Now move away further, flipped again. This is a critical piece of evidence in suggesting that the seafloor is spreading. And here you can see magnetic reversals. This would be the current geomagnetic situation. But then there's a flip. And it's found the same distance away from the center on either side, meaning that the rock is moving apart. A shifting of polarity. You can then also, if you get the age of the rock through radioactive dating, you have now a sense of how old the ocean basin is. And this is where we are today. This is the oldest part of the ocean basin along the North American coast and along the northwestern coast of Africa and a bit of the Iberian Peninsula, about 180 million years old. And as we move towards the center, we see that the ocean crust gets lighter blue to green to yellow to orange to red to the present. Amazing. And this was done by coring the rock on the bottom of the ocean, determining its age on either side of the mid-ocean ridge once it was understood that it was spreading through the theory of magnetic reversals. Amazing. Mid-60s, a global network of sensors designed to detect hydroacoustic signals, that's sound through water, was installed to monitor compliance with the Nuclear Test Ban Treaty. So we didn't trust the Soviets and they didn't trust us, so we put sensors. So if we blew up a bomb, it would be heard because that sound travels through water. The sensors also recorded earthquake activity. Scientists now find that earthquakes and volcanic activity occur almost exclusively at the edges of tectonic plates. 1968, the vessel Glomar Challenger set sail on an exploration of the mid-ocean ridge between South America and Africa. Core samples obtained from the drilling revealed that the rocks close to the mid-ocean ridges are younger than the rocks further away. Continental crust is not the same as oceanic crust. Continental crust is granitic with minerals that have a low melting point, can form a depth of 30 to 60 kilometers, more viscous and does not rise to the surface very quickly, cools faster and therefore solidifies underground rather than reaching the surface. Intrusive, coarse-grained, igneous rocks. Basalt, with minerals that have a high melting point, forms between depths of 100 and 350 kilometers, more fluid and therefore rises more quickly, cools slower and therefore reaches the earth as lava and solidifies outside of the earth. Extrusive, fine-grained, igneous rock. Past climates. Evidence that 300 million years ago, ice sheets covered South America, Southern Africa, India, and Southern Australia. If continents were in their present location, then the ice sheet would have covered the equator and the entire Earth would have had to have been extremely cold. This was unlikely scenario 300 million years ago because we also have so much fossil evidence from other locations that life was not covered by ice everywhere. Here's your Pangea. The effects of crustal movement: earthquakes, volcanic eruptions, tilted or folded rocks, sedimentary rocks at high elevations. Leonardo da Vinci, Petrarch the great poet, they were surprised to find signs of marine life up in the Alps, high in the Alps. How could that be? How could you get those fossils at the top of mountains? Fossils in rocks far from the climate of origin, such as the Glopteris plant in Antarctica. Locations of earthquakes. What do you notice? Well, if you look at your Earth Science Reference Table, these earthquake patterns match the plates either converging, diverging, or moving as transform faults. The three types of plate motion. Ocean floor. Ocean floor is not flat. Rather, there are basins, plains, and mountains. Underwater mountain chains. Ocean floor is made up of igneous rock basalt. Basalt is higher than iron, which is affected by the Earth's magnetic poles. When the lava reaches the surface, it cools, and all the magnetic materials will align with the Earth's magnetic field. This gives us a record of the Earth's magnetic field. Now, here is a beautiful map of the Pacific Ocean basin. And I will note that we have here the Hawaiian hotspot. Here's where lava is mysteriously, well, it's not really mysterious, it's for some reason the mantle is pushing up right in this section, has been for many millions of years, and this chain of mountains under the ocean are mountains that used to be where Hawaii is today because this plate is moving. So these were down here millions of years ago, and eventually Hawaii, as we know it, will move away. It will no longer be volcanic, and there'll be some area over here that moves into its place. This is the Pacific plate moving north, colliding here with the North American plate, where there's a trench because there's subduction of crust going under, and you have this volcanic activity. Where there is subduction, volcanoes. Where there is collision, continental to continental, there can be both volcanic activity and earthquakes. And where there is subduction, likewise, in trenches, it can also be earthquakes. So earthquakes and volcanoes all around this area called the Ring of Fire. So, getting back to this notion of what the Earth floor reveals. Okay, the Earth's magnetic field is reversed several times in the past. Ocean crust is much younger than the continental crust. We've been all through this. At the mid-ocean ridges, lava is creating new crust. Rocks near the center of the ridge are younger than rocks furthest. We went through all that. And again, here just to quickly show you how you can get these striped patterns. This is the way the regions will often show it on a test. Be a dark pattern and a light. Light on equal distance away from the current. This is the current situation. North is in the northern hemisphere, but occasionally it's been flipped. Then back to where we have it now. Then flipped. Then back to where we have it now. Then flipped. Equally on both sides of the ridge. Lithospheres broken into large plates. Plates are envisioned as floating on a layer of fluid set in motion by huge convection cells. Plates collide with each other, jostle past each other, drift apart. Interaction at the edges of the plate causes earthquakes, volcanic activities, and crustal movement. It is a single, unifying theory. And here is your Earth Science reference table indicating where the plates are either diverging, separating. This is a language you should know. Usually broken by transform faults along the mid-Atlantic, mid-ocean ridges. So what does that mean? That means if we go back to here, all these little crosshatches in here, these are little faults that happen as the plates are moving, spreading apart. You get these transform faults. Then you've got convergent plates. Now this little rectangle down here is very important because this is showing you that the overriding plate, right, the one going over, is the one with the rectangles on its side. This then is going under this plate. So here we have South America going over Nazca. Here we have North America going over Pacific. Here we have Eurasian plate going over Pacific. These are ways in which the plates collide. And where one plate goes under the other, we call it subduction. Subduction. And then we have this transform plate boundary right here that we can see is happening at the San Andreas Fault, a little bit down here in the Pacific, around the Scotian plate, and here in the Caribbean, causing earthquakes such as that of the one in Haiti, terrible earthquake some years ago, and there's also a lot of volcanic activity. Just note, we had the Hawaiian hotspot, the Yellowstone hotspot, the Galapagos hotspot, the Easter Island hotspot, the Tasman hotspot, the Bouvet, the St. Helena, the Canary, and the Iceland. These are all places where not necessarily associated with meeting of plates, magma's moving up to the surface. But here with Iceland, it's clearly got to do with the mid-ocean ridge. Here it's got to do with the mid-ocean ridge. Here it's got to do. But here it's isolated, isolated, isolated. So hotspots are a unique and interesting phenomenon. And yes, that's all I'll say there. Then just to note that here we have divergence where the Arabian plate is splitting from the African plate, and there's a rift here, and the thought is that over some centuries, millions of years, more than centuries, this will split apart and water will fill in here. And this may become some kind of an island arc. Types of plate boundaries and depths. I'll let you look at that if you want. Here's the folding of rock layers caused by tectonic activity. When it's folded up in a curve like this, we call it an anticline. Plunges down, and we call it a syncline at the bottom of the curve. Back up to an anticline, and then you can see there's a fold axis. There's the axis of the anticline. Here we have overturned the anticline and get a double little trouble thing here. Here we have thrusting. This whole unit here is pushing up along this unit here. This is a fault. So a fault, an anticline, a syncline. This is called a synclinal ridge, where at the top of the anticline you get a little bit of folding. And so you then can see how that what had been horizontal layers, in this case of sedimentary rock, a limestone, a shale, a sandstone, have all been folded. And we see that in the real world. This is an amazingly huge rock formation that is folded into what would be a syncline. Why do you get certain things? Well, where the plates are coming together, compressing, you get this kind of folding. And you can get a thrust fault. Where the plates are separating, pulling apart, you get stretching and thinning, and you can get a plate dropping down, a normal fault. And where you have plates moving next to each other, transforming, you can get shearing and faulting on the surface that is horizontally oriented as opposed to vertically oriented. This would be an anticline. Here's another syncline. going right into an anticline. And this could well be out in Pennsylvania, where there's a region called the Ridge and Valley Province, and if you drive around, it's in eastern Pennsylvania, you see a lot of synclines and anticlines because the rock has been folded by plate tectonic activity. This is a recumbent fold. We looked at this in Metamorphic Rock video. This is recumbent, as if you were doing a child's pose in yoga. And again, strike, slip, transform. Normal fault, divergent plates. Reverse fault, convergent plates. Strike, slips, thrust fault, convergent plates. The different types of faults develop according to whether rocks are being compressed, reversed or thrusted, or stretched due to tectonic activity and elastic rebound of crust after glacial ice has melted. This would be your strike slip on a farmyard, a big farm field in California, where the San Andreas Fault has split these ridges. Or here, the rock on the right has slipped down as the plates are pulling apart. This is a normal fault. Or here, this on the right has slipped down in relation to the left. As the plates pull apart, the rock has a weakness and it slips down. Or here, convergence. Here, this unit used to be down here. This whole thing got thrusted up this slope. Or here, another thrust. This unit used to be down here. You can see the scale. The scale here is vast. This indicates how much power tectonic activity has. And these are beautifully horizontally bedded sedimentary rocks, probably sandstones. Folding and faulting. So here we see anticline, syncline. But then we see these amazing fault blocks in here. So these blocks of rock have been shifted both up and down as they've been folded. Oh, I love this picture. I think this is from Greenland. Look at the amazing folding in here. And then these large syncline. Oh, this is just a gorgeous. Here's one of those synclinal ridges that they just talked about in the cartoon. And then you can see that what had been horizontally bedded plains of rock have been also tilted. And then you can see how without vegetation there's weathering here with when there is some kind of precipitation, debris flowing down the slope. And then I love this one with this synclinal form here and these tilted rock layers. And finally, I just wanted to show you a couple of pictures of an amazing spot in Scotland called Fingal's Cave. And these are basalt rocks that form in these amazing hexagonal pillars when they cool in just the right situations. And then, of course, through weathering over time, these have been exposed. And this is an island, again, Fingal's Cave. And then on top, there's more basalt. And on the bottom, there's more basalt. You can see. But for one period of time, the basalt that melted in to this section of the earth during some kind of mid-ocean ridge event or spreading of plates cooled in these amazing forms. And with that, we'll say goodbye.